In this section, we consider the odd and even functions. Then we look at the definition for the odd and even functions. And then we shall look at the Fourier series representation for odd and even function. Now, what do we mean by an even function? Previously, maybe you have talked about an even number, a number which is divisible by 2, an integer which is divisible by 2. But here we are not talking about the even numbers. We're talking about functions. We say that a function is even if by replacing the value x with another value of the same magnitude but of opposite side, the value of the function remains unaltered. So, for example, we may have a function like f of x is equals to x squared. In this case, when we take a value like 3 and we square, so we write f of x is equals to x squared. So when we write a value like f of 3, we get 3 squared, which is 9. If we replace 3 with negative 3, so we write f of negative 3, and we have minus 3 squared, and we know minus 3 squared is again equals to 9. So that we end up with the same value, 9, for both f of 3 and f of negative 3. Now, when the function behaves this way, then we shall say that the function is even. That the value of the function at the value of f of the function evaluated at negative x is the same as the value of the function evaluated at x for all values of x. In this case, we say that the function is even. A good example of an even function is the f of x is equals to x squared, because when we put any negative value, we square, we get the same as the square of a positive value of the same magnitude. An example of 3 is given here. We have some properties of even function. One is the graph. The graph of an even function is usually symmetrical about the y-axis. Basically, see that when you consider a function like the one we have talked about, f of x is equals to x squared, and you try to tabulate this x f of x. If you try to tabulate, we may start from minus 3, minus 2, minus 1, 0, 1, 2, 3, for example. Minus 3 squared is positive 9, minus 2 squared is positive 4, minus 1 squared is positive 1. The square of 0 is 0. Then the square of 1 is 1, the square of 2 is 4, the square of 3 is 9. So you see that this kind of a function has a symmetry at 0, because basically the values we have on this side is just the same as, it's just the reflection of what we have here. You are moving from, if you start from 0 here, moving in this direction, in the positive side, you move from 0 to 1, from 1 to 4, from 4 to 9. If you move from 0 moving to the negative side, again you move from 0 to 1, from 1 to 4, from 1 to 9. See that it's purely the same values. It's just like putting a mirror along the line. It's just like putting a mirror at 0, and you get a reflection. So if you were to plot these values, you would see that when x is 1, 2, and 3, for example, then minus 1, minus 2, minus 3, you have 1. If the value here is 1 here, 2, 4, 6, 8, 10. So at 1, the value is 1 here. At 2, the value is 4. And 3, the value is 9. This one is a curve, then 0 here. So we can draw a curve of that kind. On this side, on the other side, when x is minus 1, f of x is 1, then we have 4, some point here, then 9. So basically, if you draw this one, again you join those points, you see that it's just like putting a mirror along the line, along the y-axis. Along the y-axis here. If you just draw one side, for example from 0 to 3, and then put a mirror along the y-axis, the curve will be refracted as we have on this other side. So there is a line of symmetry, the y-axis. The y-axis is the line of symmetry. So basically what we are saying is that the graph of an even function is symmetrical about the y-axis. We have an example here. This is a graph of y is equals to x squared plus 1. So there is a symmetry. You can say along the y-axis, the left-hand side is just a reflection of the right-hand side. Now, 2 is about the area bounded by the curve between some point minus a to positive a. It is important to remember that when you are getting the integral, or basically when you looked at something like the integral from a to b, f of x dx, when evaluating this integral, we think of a curve, whichever kind of a curve, between some point A and B. Here, the equation of the curve is y is equals to f of x. And basically, we have this area under the curve, this area that we can call A. And the area of this region is basically obtained as the integral from a to b, f of x dx. So this integral is actually the area bounded by the curve, the x-axis, and some lines x is equals to a and x is equals to b. So it is also important to remember that when the region, because normally we can write, instead of f of x, we can just write y, yeah? When the region is below the x-axis, if the region of interest, say we are interested with the area of this region, then we write the area will be minus the integral from, this is the point A and this is B, from A to B, f of x dx. So that if the region is entirely below the x-axis, then we put, there is a negative here. Because the area has to be, the region, or rather the area of a region has to be positive. But in this section, f of x is negative. So if you were to work out this, you would get a negative value. We multiply by -1 to make it positive. Now, if we write an integral such as from minus a to positive a, f of x dx, we are considering a curve. It may be whatever kind of a curve. This is minus a and positive a. So it's basically the sum of the area of this region and the area of this region. I will call this one A1 and this one A2. So when we write integral from minus a to a f of x dx, will mean the integral from minus a to 0 f of x dx plus integral from 0 to a f of x dx. It's a1, it's basically a1 plus a2, the area of the region a1 here plus the area of the region a2. Now, we want to consider the case where the function is symmetrical. The function is even. Now, if f of x is even, then the curve is symmetrical. About the y-axis. The curve will be symmetrical about the y-axis. So we are thinking of, in this case, a curve. I will draw the simplest one, something like that. So that when we talk of minus a, we have minus a there and a here. Because of the symmetry, the area of this region here, which I can call A1, must be equal to the area of this other region that I call A2. So we can see that due to symmetry, A1 must be equal to A2. So when we write the integral from minus a to positive a f of x dx, we should be writing as A1 plus A2 is basically the same as 2A2. But what is A2? A2 is the integral from 0 to a. So in this case, we write 2 times the integral from 0 to a f of x dx. So when we have an even function and we are integrating from minus a to a, we can as well integrate from 0 to a and multiply the results by 2. This is because of the symmetry of the graph. This is simply because of the symmetry of the graph. So we are saying the area bounded by the curve y is equal to f of x, and the x-axis between minus a and 0 equals the area bounded by the curve, and the x-axis between 0 and a, so that when we are working out the integral from minus a to a, we just integrate from 0 to a and multiply the result by 2. We have an example here where we have the integral from minus 3 to 3. So because this curve, this function here is even, then we simply replace the lower limit by 0 and multiply the result by 2. Now we have an odd function. We say a function is odd provided that the value of the function at negative x is the same as the value of the function at x in magnitude. The magnitude is the same, but the signs differ. Say a function like if we have a function like f of x is equals to, say, x cubed, and then we take x is equals to 2, we get f of 2 will be 2 to power 3, which is 8. And when x is minus 2, we change only the sign of the value of x. We see that f of minus 2 is equals to minus 2 raised to the power of 3, which is minus 8. If you look at this 2, the magnitude is the same, but only the sign differs. It's only the sign that differs. The magnitude is the same. So when a function behaves like this, then we say it is an odd function. So you see that the value of the function at 2 is the same as the value of the function at minus 2. In magnitude, they are both 8, but the sign is not the same. The sign is reversed. The sign is reversed. So that we can write, in particular, f of minus 2 is the same as minus 1 times f of 2. When a function, if a function has this kind of a property, then we call it an odd function. We call it an odd function. So, a good example of an odd function is the x cubed. Of course, there are many other examples. And we have some properties. The graph, one is the graph. If you look at the graph and you try to, maybe you try to plot the graph of this function, f of x is equals to x cubed. If we try to tabulate and we take some values, say from minus 2, minus 1, 0, 1, and 2. I'll just take just some few values. You see that at minus 2 cubed is minus 8, minus 1 cubed, maybe I should have started from minus 3, so that we have some few more values. Let me start from minus 3, then minus 2, minus 1, 0, 1, 2, and 3. So minus 3 cubed is minus 27, minus 2 cubed is minus 8, minus 1 cubed is minus 1, then we have 0. 1 cubed is 1, then we have 2 cubed is 8, 3 cubed is 27. If you divide these two values along this point here, you see that moving from along on the positive side from 0 to 1, the value of the function becomes 1, then we have 8, then 27. Moving to the other side, we have from 0 to minus 1 to minus 8 to minus 27. You can clearly see that the values are the same in magnitude. They are equal in magnitude, but differ in the sign. The signs are opposite. The signs are opposite. So in this case, the function is odd. If you were to try and plot this, you see that some values would be, when you move to 1, 2, 3, this one should be on the positive side. This one should be on the positive side. You'll be drawing a curve. I just want a sketch. You'll be drawing something like this. But on this other side, notice the values are negative when you go to -1, -2, -3. The values of the function are negative, so it will be on this side. Something like that. So you'll be drawing a curve like this. So unlike in the case of the even function where there was the symmetry, here there is the anti-symmetry. Or basically we say that there is a symmetry at the origin. The curve is symmetrical about the origin. Or basically we say anti-symmetry. Now, this is how the function behaves. That is like a reflection about the origin. You reflect this, you do a reflection of this line about the origin. It falls to the other side. Now, if you want to, so we are saying there that the graph of an odd function, this is the graph here of the function x cubed minus 4x, which is, you can see this side, and then it comes below. This section here, looks like a reflection of this section here about the origin. So basically there is a symmetry, as a point of symmetry. The graph is symmetrical about the origin. Now if you try to find the area, or you try to evaluate now the integral, this integral from minus a to a, f of x dx. You write the integral from minus a to 0, f of x dx, plus integral from 0 to a, f of x dx. So because of the symmetry, you see that whenever you take a section here, you work out that, then on the other side you have this region here. One is the negative of the other. Remember when you are evaluating the area under the curve, as we had said here, the area under the curve, we had said above here, that if a region is below the x-axis, there is this negative. So if you were to work out this quantity here, you would actually get a negative value. We multiply by -1 because it has to be positive. Now, when evaluating this, you'll see that one of the values here will be the negative of the other. Of course, these regions are equal in magnitude because of the symmetry, but one is the negative of the other, so that when you add, you will get 0. If you are integrating an odd function between minus a to positive a, you simply get 0. So you don't even have to work it out. You'll get 0. So if you are given a problem, like the integral from -2 to 2 of x cubed, you realize that x cubed is an odd function, and the integral will be 0. You can try to check. When you integrate x cubed, you get x power 4 over 4. Then you put -2 to 2. This will be 1 over 4. 2 raised to power 4 minus 2 raised to power 4. And this will be 1 over 4 into 16 minus 16, which is 0. So in this case, you get 0. You don't even need to work it out. You don't need to work it out. It will automatically be equals to 0. This one can be done as a proof. You see that because the function is odd, you don't even have to work it out. You just need to say that the function is odd, so the integral is 0. We have some properties of odd and even function, some other properties about the products. When you multiply an even function with another even function, the result is that you get an even function. You multiply an odd function with an odd function, the result is an even function. But when you multiply an odd function with an even function, with an odd function, the result is an odd function. It's just like the case of the signs. It's just like the case of the signs where you multiply a positive quantity with another positive quantity, and the result is a positive quantity. You multiply a negative with a negative, and the result is positive. But when you multiply a negative quantity with a positive one, you get negative. So this one is analogous with the product of signs, and it's not difficult to remember that. So we have an example. A function f of x is equals to x squared sine of 2x. Now sine of 2x is an odd function. This one is odd, and this one is even. So we are multiplying an odd function with an even function, and the result is an odd function. We have here an odd function. This one is odd, and this one is also odd. You multiply an odd function with an odd function, and you get an even function. Now we have this one. X squared plus 3 is an even function. Cosine of x is also even. So multiplying the two, you get an even function. An even function. So if you multiply x squared plus 3, because that one is even, you multiply by a cosine function which is also even, you end up with an even function. Now, there are many other functions, even functions and odd functions we can get. But it is important to understand that not all functions will be even or odd. There are functions which are neither even nor odd. A function like an exponential function, f of x is equals to e raised to power x. This one is not even, neither is it odd. So it is not all functions that will be odd or even, so that when we say a function, we don't have to always start trying to view it as an even function or an odd function. There are functions which will not be odd, neither will they be even. If you have a function like f of x is equals to x plus 1, this function is not odd, neither is it even, because when you try, even you try with a value f of 3, for example, you get 3 plus 1 is 4, but when you write f of minus 3, you get minus 3 plus 1 is equals to minus 2. You can clearly see that these values are not equal. They are not equal in magnitude. So the function is not odd, neither is it even. So what I'm trying to say here is that not every function that we will try to classify as odd or even. There are functions which are neither even nor odd. Now, what we want to do is to find the Fourier series for odd and even functions. Fourier series for odd and even functions. We want to consider the case where the function is odd. So we start we want to look at the Fourier series for odd and even. Fourier series for odd and even functions. We consider a case where the function is odd. Or let's start with an even case where the function is even. So let f of x be an even function. So in this case, the Fourier series representation, the Fourier series representation is given by, we consider now the Fourier series of f of x. We write f of x is equals to a half a naught plus the sum n is equals to 1 to infinity. We have an cosine of n pi x over L plus bn sine of n pi x over L. And then we have the Fourier coefficients. A naught is equals to 1 over L, integral from minus L to positive L, f of x dx. We have an is equals to 1 over L, integral from minus L to L, f of x dx. And bn is equals to 1 over L, integral from minus L to L, f of x, sine of n pi x over L. We integrate with respect to x, and there is an error somewhere. This one is not that. It should be cosine of n pi x over L. We integrate with respect to x. These are the Fourier coefficients. Now we want to consider a special case where f of x is even.